Welcome back. This is a follow-up to the video about unit tangent vectors and unit normal vectors. Um, this isn't quite part 2 yet. This is just filling in some things that may have been a little bit convoluted that I said. When I was talking about acceleration being normal in the example that we had, so in other words it was all centripetal acceleration, I thought it'd be nice to cover a case where there's some tangential acceleration as well. That way we can figure out what components go in what direction. So here we have a parabolic parametrization of that the position of t, the vector equation, is given by the x component as a function of t and the y component is a function of t squared. And so while the x grows constantly, the y accelerates, as you can see there with the t squared. So I have drawn here in red the vector, which remember vector is, this is velocity, and velocity is always tangent. It's always tangent to the position curve. So we know that velocity equals the change in position with respect to time. And that's dr dt. So we differentiate each component here and we get 1 in the x direction and 2t in the y direction. You'll notice that the x velocity is constant, but the y velocity is increasing, which means that there's some acceleration. And it may not all be centripetal. So the next step is to figure out what even is the acceleration. And to do that, we take the second derivative with respect to time of each component, otherwise known as d2r over dt squared, which is also equal to dv dt, so we'll just take the derivative of these two components separately. And the derivative of a constant velocity is 0. The derivative of 2t is 2, which means that we have, at any point on this graph, 2 meters per second of acceleration straight in the y direction. You'll notice there's no acceleration in the x direction. Let me go ahead and write this in meters per second. Let's write this in meters. That way we know that there's 2 meters per second squared acceleration straight up. And so you'll notice I have this acceleration drawn here, which represents the total acceleration. And you may notice that it does not share a 90-degree angle with velocity. So in other words, the acceleration isn't orthogonal to velocity, at least not all of it. So the next step here is we found our acceleration. Now we're interested, how much of this acceleration is centripetal, otherwise known as a sub n, also known as a radial, or anormal. So there's several different terms for that. It could be centripetal, normal, or radial acceleration. And then we're also looking for the acceleration tangent to the velocity. So the acceleration that's parallel with velocity. And so to do that, we're going to find our unit tangent vector, which remember, velocity gives us our tangent direction. We divide by its magnitude to make it of length 1. That gives us our unit tangent vector. And it looks something like this. The next step is to do a projection of the acceleration, which we solved for right here. We solved for the acceleration here. And that's this acceleration, the total acceleration. Now if we do a dot product with the unit tangent vector, what we are essentially doing is we're taking, let's draw this in a different perspective. Let's say this is your total acceleration, and this is your unit tangent vector. So anything multiplied by 1 is the same thing. So when we take the dot product between a and t, what we find is we find the amount of a that is in t's direction. So we're looking at the amount of a that's in the t direction. That's acceleration tangential. So what we've done here is to find acceleration tangential. We've taken the total acceleration, which we solved with differentiation, and dotted it with the unit tangent vector, which has length 1, therefore giving us a perfect projection of acceleration tangential. So now that we know acceleration tangential and we know acceleration, there's going to be a Pythagorean identity involved here. And so, as you'll notice, A is the hypotenuse of a triangle that has AT and AN side length. And so if we want to solve for AN, we can use the idea that the hypotenuse squared equals the opposite squared plus the adjacent squared. Therefore, we can reorganize this and find that the normal acceleration, otherwise known as the radial or centripetal acceleration, is equal to the square root of the magnitude of a squared minus the magnitude AT squared, acceleration tangential squared, all under the square root. And so I hope this clears it up for cases where there is tangential acceleration. This is why we always use the unit tangent vector to derive our normal vector and not just our acceleration vector, because acceleration, if there's any tangential velocity, will not be orthogonal to our tangent line. So I hope that was helpful, and I'll see you next video.